Good morning, all. My name is Kiran and I am from ECU. Today I am going to explain dual simplex method and we will see the procedure, numerical example, algorithm, and code in MATLAB application. Before going to dual simplex method, we will see some of the differences between simplex method and dual simplex method. Simplex method starts with basic feasible solution and proceed towards the optimality. In dual simplex method, it starts with basic infeasible solution but optimal solution and proceed towards the feasibility. See here. Feasibility to optimality, we will use simplex method. While in optimality to feasibility, then we will use dual simplex method. Advantages of dual simplex method. In dual simplex method, we will not require any artificial variable in the constant. If any artificial variable will be present, then we will use two-phase method and decay method. If any artificial variable not there, then our complexity of the problem will be reduced and we will easily solve the problem. Now we will see the procedure of dual simplex method for maximization type problem. If any given problem is in of minimization type, then we will convert it into maximization type by multiplying with -1 for the objective function and convert each and every constant of greater than or equal to type into less than or equal to type and transform every less than or equal to type constant into equality constant by adding a slack variable to it and add a zero cost function to the objective function. Now, so step two, find initial basic solution. By setting zero value to the decision variable, we get initial basic solution. Now, for optimality condition, in simplex method, we are first selecting a column based upon the value of Cj minus Zj. The maximum Cj minus Zj value we will select as a key column. And for getting a pivot element, we will also select a key row. Based upon the minimum ratio test, we will finding the key row in a simplex method to get a pivot element. After selecting a pivot element, we will make the pivot element 1 and rest of the elements are 0. This is our iteration in simplex. While in dual simplex, first we will select a row based upon the value of xb. Yeah, the most negative xb will select as key row, and after selecting a key row for getting a pivot element, we will select a key column based upon the value of Zj minus Cj by key row, and key row must be less than 0. This is our key column and we will iterate our after getting a pivot element make the pivot element as 1 and other elements are 0, then we will perform iterations and after reaching all xb greater than or equal to 0 and z minus cj greater than equal to 0, we'll stop the process and that is our desired solution. Now we will see the numerical example over here. Minimum z is equal to 5x1 plus 6x2. That is our objective function and constraints are x1 plus x2 greater than or equal to 2 and 4x1 plus x2 greater than or equal to 4 and non-negative restrictions are x1 x2 greater than or equal to 0. Now we will convert every minimization type problem into maximization type problem by multiplying with minus 1. That is z is equal to minus x1 minus 6x2 and every greater than or equal to constant should be converted into less than or equal to type constraint and after converting less than or equal to type constraint add a slack variable. Uh, After adding slack variable the constant must be this type and we will add a zero cost function to the objective function and these are the non-negative restrictions. Initial basic feasible solution is given by x1 is equal to 0, x1 is equal to x2 is equal to 0, then s1 is equal to minus 2 and s2 is equal to minus 1. We will perform the operation iterations over here. Zj minus Cj for getting a key column and first we will select a key row. How we will select a key row? Based upon the value of xb. What is the most negative xb? Minus 4. Then this is key row and now we will select a key column based upon the value of Zj minus Cj by that key row and key row must be less than 0. We will make maximization and we got maximum of minus 1.25 and minus 6. This is minus 1.25. We'll get a pivot element as uh, minus 4 and we'll make some row operation and make it as 1 and 0, performing iterations and our last iteration would be this. and we will get all xp greater than 0 and zj minus cj value greater than 0, and we have x1 x2 and x2 will not then this, so we will take at 0, and max z is equal to cb into xb. We will perform maximum z, minimum z is equal to minus max z. We will get the value of minimum 10. Now we will see the CAN protocol, where our application in dual simplex is CAN. Now we will see the architecture: CAN high and CAN low. These are the nodes of CAN and CAN bus. CAN is a communication-based protocol and used in the field of embedded system and industrial automation. It was developed by Robert Bosch in 1980s to provide a reliable and robust method for transmitting data between electronic devices in vehicles. CAN is a message-based protocol, and the identified species, the message priority, and devices with lower priority messages will wait until a higher priority messages have been transmitted before transmitting their own messages. This is basic idea of CAN, and applications of CAN was automotive system, industrial automation, medical devices, robotics, aerospace, and defense. Now we will see dual simplex in CAN protocol. Suppose we have a CAN network with 10 message IDs available for allocation and 3 devices that need to be assigned IDs. The devices are as follows. Device 1 requires 4 message IDs, device 2 requires 3 message IDs, device 3 requires 2 message IDs. We want to allocate the message IDs in a way that minimizes the total number of IDs assigned to devices while ensuring that each device is assigned a unique set of IDs. Now, our objective function is minimization z is equal to x1 plus x2 plus x3, and our constraints are x1 plus x2 plus x3 less than or equal to 3, and x1 less than or equal to 4, x2 less than or equal to 3, x3 less than or equal to 2, and non-negative restrictions are these: x1, x2, x3 greater than or equal to 0. Now, this problem can be solved with the help of dual simplex. Same, we see the previous example in dual simplex. Same, we have three steps of dual simplex and procedure, and then one numerical example over there. Same, we'll implement this in MATLAB. Input data was this: n is equal to 3 and m is equal to number of devices, number of message IDs, objective function coefficients, and cost matrix. Right hand side, RHS side. Initialization was this, and dual simplex, optimality conditions check, and entering variable. These all we will see in procedure and step lengths and leaving variables. This code is in MATLAB, and I have taken these in references. Thank you.